Everybody, today we're jumping into section 3.3, implicit differentiation. And implicit differentiation allows us to find the derivative of y. Oops. When we can't solve for y. So let me show you how it works looking at a problem where we can solve for y, and I'll go ahead and do that. So, for instance, suppose I have a problem and it says find dy dx. So I'm trying to find the derivative of y with respect to x. And say the problem gives us y plus 3x squared minus 5 equals 0. So there's my problem. Now, what we've done up to this point is we've always had y by itself. So they'd give us the function. If I solve that for y, I'm going to subtract the 3x squared from both sides. I'm going to add the 5. I'll get that. Now, this is a function in terms of y. So I'm going to do what I've been doing the whole time, and this would be explicit differentiation. And that's just taking the derivative the way I know how to. So I'm going to say, oh, dy dx is just negative 6x. Done. But suppose I couldn't solve for y. So let's leave it in the form we have over on the other side, and we'll find the same derivative, but using implicit differentiation. So here's the idea. Here's what we do. Let's write this problem down again. Y plus 3x squared minus 5 equals 0. I'm leaving a little room there because what I'm going to do is I'm going to say, hey, let's take the derivative with respect to x of both sides. Now remember, with the derivative of the sum or a difference, I can take the derivative individually and then add or subtract as appropriate. So I'm going to first take the derivative with respect to x of this y. Then I'm going to take the derivative of 3x squared. Well, I know that's 6x. And then the derivative of 5. Well, that's just 0. And then the derivative of 0 is also 0. But the derivative with respect to x of y, that by definition is dy dx. And so now I've got dy dx plus 6x equals 0. I subtract the 6x from both sides. And I get dy dx equals negative 6x, which is exactly what we set up here. So we know we have the right answer. But that key was when we took the derivative of y with respect to x, that is dy dx. That is the derivative of y with respect to x. That's what we call it. Okay, so now let's go from there and show you why this is needed. Here's the problem. The big problem is, write this as a note. Y is a function, not a variable. When we are finding dy dx. So that derivative. Okay, so suppose I was taking, for instance, think about this. Say I'm trying to take the derivative with respect to x. And let's say it's something like 5 times x squared plus 1 to the 4th. We know how to take the derivative of that. We use the power rule. We bring the 4 down, multiply by the 5. So we're going to get 20. The x squared plus 1 stays, raised to the 3rd power. But then we'd say, oh, chain rule times the derivative of the stuff inside. So the derivative of the stuff inside is the derivative of that x squared plus 1. And we know what that is. That's 2x, but that's not my point here, is that we're doing the chain rule. We're doing the derivative of the stuff inside. Because suppose I don't know that's an x squared plus 1. Suppose y was equal to x squared plus 1. Unknowns to us. All we know is y is some function. Well, maybe the function is x squared plus 1. I don't know. But what would happen, this same problem, instead of saying d dx of 5 times x squared plus 1 to the 4th, is going to just say 5y to the 4th. If I substitute that x squared plus 1 in, I get that previous problem. Now when I take the derivative, think of what I do. I do it the same way. Use the power rule, 4 times 5. I get 20 y to the 3rd, but then times the derivative with respect to x of whatever y was. I don't know y in this case. So what I have to call that, I say, oh, that's dy dx. That's the key to what we're going to do when we do implicit differentiation. If I'm taking the derivative with respect to x, and there's any other letter in there, y in this case, when I take the derivative of that y, I treat it as a function, and so I have to do the chain rule and then multiply it by dy dx. So this dy dx is always going to come up when I'm taking the derivative of a different variable than what I'm taking the derivative with respect to. In this case, d dx. I have a y, not an x, so I have to attach the dy dx. So let's do a few examples of this to see how this plays out. So I've just picked several problems from the book. So the first problem we're going to do is actually problem 4. They say, find dy dx. The problem actually says, differentiate implicitly to find dy dx. But that's what we're going to do anyway. So the problem is x squared plus y squared equals 25. And so the idea is I'm going to take the derivative of each side, just like I did before. So we're going to say, hey, let's take the derivative with respect to x of each side. Now, when I take the derivative of x squared, what I get, as always, I just get 2x. Plus, now when I take the derivative of y squared, remember y is a function. So I still do similar to that x squared. I say it's 2y, but I say, oh, wait, y is a function. So the chain rule is going to say times the derivative with respect to x of whatever y was. So times dy dx. That's the derivative of the inside function. I didn't have to do that with x because x was the variable. I had to do it with y because y is a function. And then on the right side, the derivative of 25 is just 0. What I'm trying to do is get dy dx all by itself because that will be the derivative. So I'm going to subtract 2x. So I get 2y dy dx equals negative 2x. And then I'm going to divide by that 2y. I'll even write that down for you. So I'm going to divide both sides by 2y. And then on the left-hand side, all I have left is dy dx. I can cancel the negatives. I just get negative x over y. And that's my answer. There's my derivative. I still haven't solved it for y, but that's okay. What this is telling me is when I take the derivative, remember that's the slope of the tangent line. The slope depends on not just the x variable, but also the y value as well. And so what we'll do is we'll do a problem where we plug in an x and y to find out actually what the slope would be at that point. Now notice x squared plus y squared is 25. That's a circle, centered at the origin, radius 5. But it's the tangent line at any given x, y value. All right, so let's jump to another problem. This is problem 16. It's going to be similar to that, except we're going to plug in a value. This one says find dy dx. And then find the slope of the curve. Remember, the slope of the tangent line and the slope of the curve are the same thing. then find the slope of the curve. They're the same value anyway. They represent different ideas. At, and in this problem, they give us the point 2, -1. Okay, so there's my problem. The function they give us, x cubed plus 2y cubed equals 6. So we do the same thing. We take the derivative with respect to x on both sides. Now, if you want to, I often, instead of rewriting the whole problem, we'll just do it this way. You're welcome to rewrite the problem, but we can still see what the original problem is. Since I have a different colored pen, I'm not afraid to do that. So I can see what the original problem was. And then I can see, oh, I added the derivative with respect to x to both sides. So again, when I take the derivative of x, it's just the way it always is, 3x squared. Plus, but when I take the derivative of y, 6y squared times from the chain rule, the derivative of whatever that y is. Well, that's dy dx. Because I don't know what the derivative of y is, but it's dy dx. Again, equals 0. I'm going to subtract the 3x squared from both sides. I'll show more steps this time. Next time I will not. You can probably do this mostly in your head. That's not a very good x, is it? Let's clean that up a little bit. All right. And then, of course, I'm going to divide by 6y squared. And so on the left, I just get dy dx, which is the derivative. Well, I can reduce the 3 goes into the 6 twice. So I get negative x squared over 2y squared. There's my derivative. And if I want to evaluate it, we'll just put it right here. Dy dx evaluated at, and what they give us, 2, -1. Remember, the 2 is the x, the -1 is the y. I just plug it in. So it's negative, and then 2 squared over 2 times -1 squared. Well, that's negative. The top is 4, the bottom is 2. So I get an answer of -2. That's my slope of the tangent line at that point. It's also the slope of the curve at that point. All right, so that's the idea. They do get a little more difficult. The difficulty comes when I've got x and y's in the same piece, so in the same term. So let's look at a couple of those. Problem, well, the third problem I'm going to do is actually back to problem 2 in the book. It's 2xy. Let's see what the problem tells us to do. So the problem again says find dy dx. And it says implicitly, but we'll just go ahead and do it. 2xy plus 3 equals 0. All right, again, I'm going to take the derivative. Oh, I wanted to change the color there. I'm going to take the derivative with respect to x of both sides. All right, now we need to be careful because this is 2x times y. I need the product rule here in this piece. Remember the product rule, we'll write it over here. The product rule is the first times the derivative of the second plus the second times the derivative of the first. Well, all right, let's do it. So I'm using the 2x as the first, and I'm using the y as the second. Okay, so I do the first 2x. Let's change that back to the black pen. The first times the derivative of the second. Well, the derivative of y is just dy dx. You may say, well, the derivative of y is 1, and then do the dy dx. If you want to put the 1 there or not, if it helps, go ahead and put it. Because if we did the derivative of x, we'd just say a 1. That's where that 1's coming from. Or you could just say, wait, the derivative of y with respect to x is just dy dx. Either way, you're right, but either way, you need both of those there. So there's the first times the derivative of the second, plus the second times the derivative of the first. Well, when I take the derivative of 2x, it's just 2. So that was my product rule. First times the derivative of the second plus the second times the derivative of the first. And then the 3, the derivative of that, of course, is 0, and then equals the derivative of 0, 0. All right, so I've got a lot of stuff written there because I've written that product rule there. So let's go ahead and erase that product rule piece so that we can not get as confused when we go to the next step. Okay, so I'm going to subtract the 2y from both sides. So this first piece is just 2x dy dx. And then I'm going to subtract the 2y, so I get negative 2y. And then I'm going to divide by the 2x. We'll write that there since I'm going to reduce anyway. And I get dy dx equals, the 2's cancel, negative y over x. Done. So we had to use the product rule this time because we had x's, y's together in one piece. All right. So again, let's try another one of those. This time we'll have values to plug in to find the slope of the curve. All right, so this is problem 23. As you notice, I'm jumping all over the place. I don't really think the author did a great job of putting the problems from easier to more difficult. So I just kind of skipped around. I helped him out. So find dy and slope of curve at, and on this problem, they give us negative 2, 1 again. You'll notice this author usually gives us pretty small numbers for the x and y to plug in. Okay, so the function this time is x to the 4th minus x squared y cubed equals 12. And again, so what we're going to do, we're going to take the derivative with respect to x both times. So when I take the derivative of x to the 4th, I just get 4x cubed minus product rule. So I've got another product rule here. So it's the first times the derivative of the second. Now, since I'm taking the derivative of y, that's why I have to attach that dy dx. Plus the second, y cubed, times the derivative of the first. Well, the derivative of x squared is just 2x. But I'm putting that in brackets or parentheses because I want to remember to distribute the minus, and then equals 0. All right, so let's get rid of that by distributing the negative. So we've got 4x cubed minus 3x squared y squared dy dx plus 2xy cubed equals 0. And remember, I'm trying to get dy dx by itself. So everything that doesn't have a dy dx attached to it, I'm going to move to the other side. So I'm going to subtract away the 4x cubed and the 2xy cubed. So I'm getting it negative 3x squared y squared dy dx equals negative 4x cubed minus 2xy cubed. And then I can divide away the negative 3x squared y squared. And I'll be left with just dy dx on the left side. Now, if we want to, we can factor out what the greatest factor is on top and bottom to cancel it out. So think about what I can cancel out. I can cancel out a negative. The only thing that they all have in common other than that's the x. So I'm going to factor out a negative x on top and on bottom so that it'll cancel out. So I'm going to get 4x squared plus, because I factored out the negative, and I factored out the x, 2y cubed. And on the bottom, I factor out an x. I still have positive 3xy squared. But now those negative x's will cancel out. Let's put that back in there. Oops. All right, so that's what I had. Those negative x's canceled out. So I get dy dx equals 4x squared plus 2y cubed over 3xy squared. It's a mess, but that's my derivative. And now when I want to evaluate it at the point they gave me, and what they give me, 2, -1, -2, 1. So dy dx evaluated at 2, -1. Is that what it was? 2, -2, 1. I thought I might have messed that up. -2, 1. So I get 4 times -2 squared plus 2 times 1 cubed over 3 times -2 times 1 squared. All right, let's see what that is. So the 2 squared, -2 squared is 4, so I get 16 plus 2 on the top. And on the bottom, I just get -6. So it's 18 over -6, which gives me -3. That's my slope of the curve at that point. All right, so that one came out nice. A lot of times it won't come out as nice, but that one did. The dy dx doesn't look very nice, but when I plugged in that point, it came out nicely. Okay, that's most of it. The only thing we haven't looked at yet is what if we have more than one y in the problem? So let's do a couple of those, and we'll see what the trick, if you will, is there. Okay, so let's look. This is actually problem 1, which I don't know why he gives this to this as problem 1, because it's a very difficult problem to start off with. Because I've got x squared plus 2xy equals 3y squared. And the difference between this and the other problems is we see y in 2 different places. We approach it the same way. Again, they're just saying find dy dx. They say implicitly, but I would have a hard time getting y all by itself. It would be a mess. So we take the derivative implicitly. So let me write it again so I can fit in that dy dx on both sides, since I didn't leave much room. So I'm going to take the derivative with respect to x on both sides. Again, when I take the derivative of x squared, it's just 2x. The 2xy, though, I have to use the product rule. So I go plus the first times the derivative of the second. Remember, that's a y, so we have to do the dy dx. Plus the second times the derivative of the first. Well, the derivative of the first is just 2. So I was just putting the dot right there. So I'm using the 2x as the first and the y as the second. Equals, now on the right side, the derivative of 3y squared, 6y to the first, but it's y, so the chain rule says times dy dx. Remember that dy dx is always just the chain rule, because I'm saying, oh, times the derivative of y. I don't know what it is because I haven't solved for y. We call it dy dx. But now the problem is I have dy dx in 2 different places. The key is we need to get them on the same side and factor out the dy dx. So anything that doesn't have a dy dx, we want on the other side. So watch what I'm going to do. So this 2x that I have to begin with, I'm going to move it to the other side. It's going to become a -2x. So I subtract it. The y times 2 at the end, I want to subtract that also. So I'm going to do a -2y. Now, I've got this 2x dy dx. I'm going to bring that 6y dy dx over, so I'm going to subtract it from both sides, and I get a -6y dy dx. All right, so all I did was, you can either just move it across the equal sign and change signs, or you're adding and subtracting as appropriate. I guess all we did was subtract from both sides. But the reason I do that is because now I'm going to factor out this dy dx. And it's going to leave me with 2x minus 6y equals -2x minus 2y. And now all I have to do is divide that 2x minus 6y away, and I have dy dx by itself. Now I will tell you what authors like to do. They like to get rid of negative signs. So what they're going to do is they're going to factor out a negative. And since 2 goes into everything, they're going to factor out a 2 also. both top and bottom. Factor out the same thing, top and bottom, so they'll cancel out. So I'm going to end up with x plus y on the top. And on the bottom, since I factored out a negative 2, it's actually negative x plus 3y. They're actually going to change that order and make it 3y minus x. So now these negative 2's cancel out. And they're going to write the answer as that x plus y on the top. And the bottom is just going to be the 3y minus x. They typically write it that way because they get rid of as many negative signs as they can, and they don't like to lead with a negative, so they didn't like the negative x plus 3y. That's typically how you'll see the answer in the book. All right, so that's essentially as hard as it gets because we have to do the dy dx whenever we take a derivative with respect to y. We had a product rule in there. And we also had the fact that we had 2 dy dx. We had to get them together and factor them out. So that's as tough as it gets. Do one more of these where we plug in values at the end. It's problem 25. Find dy dx. I'm just going to say this time and evaluate at 1, negative 2. So as you see, a lot of the same values there. And what they give us this time, they give us xy plus y squared minus 2x equals 0. So I'm going to leave a little room for the equals 0 so I can slide in my d dx on both sides. So we're taking the derivative with respect to x on each side. And this first piece, we're going to use the product rule. It doesn't look like a P, does it? It looks like I almost wrote chain rule. So this first piece, we're going to have to use the product rule because there's x times y. None of the other pieces have that, so just that piece. So when I take the derivative, the first x times the derivative of the second. Well, that's either just dy dx or it's 1 dy dx, your choice. They mean the same thing. So that's the first times the derivative of the second plus the second times the derivative of the first. Oh, the derivative of x is just 1. And again, I don't have to do the dy dx because that was x. That's what the variable is, d dx. Plus, now when I do the y squared, it's 2y, but then the chain rule says, oh, times dy dx because y is a function, not a variable. So I have to take the derivative of y, whatever it is. And then the minus 2x is just the derivative, that's minus 2. Equals 0. Again, I have 2 dy dx's. Everything else I want to move to the other side. I like to do this all in one step, but I'll do it in 2 steps. So I'd move the stuff over and factor out the dy dx at the same time. We don't need to do that. So anything with a dy dx, I'm going to leave over here. So I've got an x dy dx, and I've got a 2y dy dx. That y times 1 is just y. I'm going to subtract it from both sides, so I'll get a minus y. And that minus 2, I'm going to add to both sides, I'll get a plus 2. Again, they're going to switch that around, make it 2 minus y. That's what they do. So now I'm going to factor out the dy dx, and I get x plus 2y equals, now let's switch that around, 2 minus y. And then I'm just going to divide away the x plus 2y, and I'll be done. Then I can plug in my values. This time I've already factored everything out. There's nothing to reduce. It's just 2 minus y over x plus 2y. There's my derivative. And then we'll go ahead and evaluate it again at 1, negative 2. And so I go, oh, it's 2 minus negative 2. And it's 1 plus 2 times negative 2. Well, the top, of course, that's 2 plus 2. The bottom, 1 minus 4. So I get 4 over negative 3. And you can leave it that way. You can write it as negative 4/3. They mean the same thing. Your choice. You can even write negative 4 over 3 if you want to. But anyway, that's the idea. The big key is whenever you take the derivative of x, you just take the derivative normally. But when you take the derivative of y, you take the derivative but then you have to say times dy dx. And that's it. If you have more than one dy dx, you get them to the same side, factor them out, and solve. All right, so practice these. That's actually the end of what we're going to do in chapter 3. All right, so practice that. I think you'll be able to get it. And just go ahead and ask if you have questions. And best of luck with that, and I'll talk to you again soon.